Okay, we are back. We are talking about the photovoltaics, and in this section we are going to talk about the PV systems. And so let's look at this. These are the topics we are going to cover. First we talk about how a PV module is made, and then look at the module IV characteristics, and then we will see how the PV arrays are constructed from the PV modules, and we look at some of the key parameter influences on the arrays. The first one is the temperature effect on the IV characteristics. In doing so, when you're going from cell to module to arrays, we have to make sure that they are protected from one of the cells going bad and things of that nature. So we use what is called bypass and blocking diodes. So pictorially, what these topics are shown here. You start out with a cell. Typically, the cell is around 10 centimeters by 10 centimeters, and then you put bunch of them together to make the module, and then you put the modules together to make an array, and you put arrays together to make a system. And that is how we are going to proceed in this section. So first thing we want to consider is cells to a module. Typical module picture is shown here. This one produces about 308 watts of power when it is exposed to 1000 watts per meter square at standard room temperature of 20 degrees C. And this has, for example, has 96 cells in it. So you can count them, for example, here, and this makes as one cell. This first one here, this is as one cell, and like that you can see there are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these like this, and in 8 in this way. So total we have 12 by 8 array here, and that will make 96 cells. So when you look at the output of a single cell, which we have seen before is condensed now, you start out with the short circuit current for the cell. I mean, that is not going to change. And then you have the IV curve which is coming here down, and this is about 0.7. Let me use this. This essentially gives you 0.7 volts. So that is for the one cell. So like that you put them in series and parallel. So when you work adding cells in series look like this. So when you add them in series, what you are trying to do is increase the voltage. So if you have 96 cells, then the voltage, open circuit voltage, goes to around 21.6 volts. And here in this figure, it's only about 36 cells here, and they're about 0.6 volts. And so we are putting these cells together in series. So when you put them in series, you increase the voltage and the current remains the same, and typically this is around 4 amps or so in this particular case, and you multiply by this, you get about 100 watts or so in this particular panel. So that is how we do this. So typically in this particular case, when you put 96 cells, like the panel which I have shown here, it has give about 54.7 volts, and then current is typically around 4, and are depending on what you do, you can get close to about 308 watts of power out of this panel. So one of the important things you want to do is when you put these things here, suppose you have one of these cells goes bad. Imagine that this one is gone bad for some reason. Now when a cell goes bad, this of course will put a resistance into the system. So then the whole panel gets affected. To avoid that problem, what we call is a blocking diode. We put a diode, and diode will allow the current to flow in one direction. So even if it fails, you can bypass this, and rest of the module will work properly. So this is so it is important to put blocking diodes between each of the cells. Of course, it depends on the manufacturer. Typically they don't do that. What they do is they bunch them together, so about 4 by 4 or something, then put a blocking diode. otherwise the cost becomes too prohibitive. But it's ideally what you like to do is you put a blocking diode between this cell and the next cell which is connected to it. So the characteristics then would be the voltage across the individual cell is given by this. We have done this before. This is the diode current minus any resistance we have. This is the series resistance in this particular case. So when you substitute for V sub D, and this is what the expression for that is, and then you for the current you have this. In here you have the resistance when it is in parallel. So the voltage for the series is given by this, and the current is given by this for a typical cell. But when you get to the module, the voltage, this is the voltage of the entire module. So this is how many number of cells you have, and then you still have this voltage which is same as the given here. So if you have, for example, 100 cells, 100 times whatever this voltage, which is about 0.7, then you get 70 volts or so. So this is how you, then the current of course is not going to change significantly from that. Now if you want to increase the voltage, you do in the array. So same thing what we did for the cells. You have one module here in this case, and we put them in series, and then another module here. So you have, for example, you have 50 volts here, and another 50, 150, then you have another 50, about 200. So if you want to get, for example, 200 volts voltage, then you can essentially put them in series, and that's what you do when you increase the voltage of the array. Then when you want to increase the current, typically like we get 4 amps, you can't do much with 4 amps. Typically a house electricity needs about 15 amps or so. Then what you have to do is you have to orient these, connect these modules in series. Then you get when you put them in series, then you add the currents together. So when you want to get increase the voltage, you put them in series. When you want to increase the current, you put them in parallel. So then you have one module, 2 and 3, voltage will remain the same, but you have the current is going up. So what you typically do for array is combine these two things. So now we have series of 3 modules, which is what we have 3 of them here, and they are in series, and 2 of them in parallel. So what you have here, this is the 1, for example 2 and 3 will give you the voltage. Now you have this one here and this one here in parallel will give you the current. So in this particular case, you not only increase the voltage, you also increase the current, and so the net output will be what you desire for the application. And this is one way to connect it. The other way to connect it is to put 2 in parallel and then connect that into this that of a thing. So it depends upon how the strings are made. So these are called the strings, and in one case you have 3 of them in parallel in series, and 2 of the arrays are put in parallel system. So this is how you connect these systems to get the desired voltage and desired current. So when you do this, one of the important things you worry about is what happens when the temperature, that is the ambient temperature, changes. In fact, this becomes an important thing in places like California or Arizona, where in the winter time the temperatures are very low because these things are installed typically in desert climates, and then in summertime they get very hot. So the temperature can vary anywhere between 10 degrees Fahrenheit to about 110 degrees Fahrenheit. So one of the things we want to know is what is the effect of the temperature on this. So here, for example, the data IV plot is plotted for 0 degrees C and 25 and 60 degrees C. And there are 2 sets of curves here. This is a curve for the insulation is about 1000 watts per meter square. This is intensity of the radiation, and here it is shown for 500 watts per meter square. The first thing you notice is for all the temperatures, the current changes very little. So you can see the change in the current with increasing temperature is not much. But however, there is going to be a voltage change here. You can see that in this particular case the voltage changes from about 17.5 to about 22.5. So there is a significant change in the voltage with the temperature. So the effect of the temperature on the module is simply a change in the voltage, not much in the current. So for crystalline silicon cells, the voltage drops about 0.37% for each of the degree C. So increase in temperature on the in terms of the current is very little. There's less than 0.05%. So the net result in the drop in the maximum power is about 0.5% of for the degree C. So that is what you expect. So then you can multiply that. So let's say you have a 20-degree difference. 20, that is about 20 multiplied by 5. That's about 10% variation in the power, and that you can put it in the equation form. This is the change of temperature, the change of the open circuit voltage with temperature, and that is given by this formula here, which is minus 2.3 times n sub c is the number of cells, and of course this is in millivolts. So let's say we have 100 cells in the module, then you have 2.3 times 100, that's about 230 millivolts for degree C. And the current, of course, is a much smaller change in the current. This is the short circuit current, and here the units are microamps. So this is in millivolts and this is in microamps. So there is a very small change in order of magnitude, in fact 2 orders of magnitude reduction in terms of the change in the current as compared to the voltage. And the way you can calculate that, for example, when you look at the different intensity of the solar radiation, this is the short circuit current at a particular G is given by, let's say for example you have 500 watts here, you multiply that one by the ISC at 1000 watts per meter square, that's where things are generally calibrated at, and multiply by G, which is in kilowatts per meter square. So if you want to find out, for example, at 300 watts per meter square, what should be the current, and typically you take the value given in the standard conditions, and that is what is given in the specific spec sheet, and multiply by that value G, and then that is what you get for the current. And for the voltage, of course, you have the maximum power point voltage, which is 80% of the open circuit voltage, and this value are given in the specification sheet of the module. So by knowing these two values, then by knowing the insulation, you can then calculate I sub SC and the maximum power point, and you multiply these two, then you get the power at the maximum power point, and that is what is or sometimes it is called W peak power. So watts peak they call it, and so that is what these two numbers you multiply it to get that value. So from this you can calculate what the losses of the temperature are. And typically there is another quantity which they give in the spec sheet, is called the normal operating cell temperature. So it is the cell temperature when the module is operating under the following conditions at open circuit. So this is irradiance is given, these are the standard conditions under which they are tested. So the insulation is about 800 watts per meter square, and spectral distribution used is AM 1.5, and cell temperature is 20 degrees C, and the wind speed is 1 meter per second. So usually this temperature is between 42 to 46 degrees C. So this is typically given by the manufacturer in the spec sheet. So this is, you remember that we talked about cells get hot because of inefficiency, and you can see that value in here. So during the module operation then, cell temperature is given by this value here, that's the operating cell temperature. This is the ambient temperature, which you know, and normal operating cell temperature is given by the specifications of the module, and that's divided by minus 20 divided by this factor, efficiency factor, and multiply by the insulation. So essentially from here you can find out what is called the cell temperature, T sub C. And G, which is given insulation in terms of kilowatts per meter square. Typically that means it's about 1 kilowatt per meter square when full sun, and then if it's 0.5 and so forth. And the TC are the cell temperature and the ambient temperature respectively. So you can calculate the cell temperature by knowing the normal operating cell temperature and the ambient temperature and the insulation. And these are of course known quantities, and then from that you can find out the solar cell temperature. And this is how you calculate these temperatures. So from here you can now know for a given module, and given these temperatures and the insulation, you can calculate the performance of the IV. Okay, thank you.